In this section, we have two objectives. We're going to be solving exponential equations and we're going to be solving logarithmic equations. So let's go ahead and get started with example number 1. So we wish to solve 2 raised to the 5x is equal to the number 64. So the inverse of an exponential base 2 is a logarithm with base 2. So we're going to use the fundamental property of equations, which says if I do something to one side of an equation, I have to do the same thing to the other side. So I'm going to have the logarithm base 2 of 2 to the 5x is equal to the logarithm base 2 of 64. Well, since the logarithm base 2 and the exponential base 2 are inverses of each other, they reduce out. And on the left-hand side, the only thing that's left is 5x is equal to the logarithm base 2 of 64. Well, it turns out in this case, that simplifies nicely. We can go alpha window and choose choice number 5. And if we do the logarithm base 2 of 64, we end up with 6. So now, after using the logarithm, or the inverse, on both sides of the equation, we've now reduced this to a linear equation, 5x equals 6. So now we just get x by itself by dividing by 5, and that gives us x is equal to 6/5. All right, let's take a look at our next example. So we wish to solve the equation 5 to the x is equal to 6. So we're going to do the same thing. So what would be the inverse of an exponential base 5? Well, it would be a logarithm base 5. So we do the same thing to both sides of the equation. So we take a logarithm base 5 of both sides. So we have a log base 5 of 5x equals log base 5 of 20. And those are inverses, so they undo each other. And we get x is equal to the logarithm base 5 of 20. So in this case, we don't do anything to the logarithm base 5 of 20. Because we could approximate it on our calculator if we wanted to. If we go logarithm base 5 of 20, we end up with 1.86. But most of the time, unless we are asked explicitly for a decimal approximation, we'll want to leave our answer just like this in terms of an exact answer. And so this is our preferred way to write our solution, unless we're asked for a decimal approximation explicitly. All right, let's take a look at our next example. So on example number 3, we wish to solve the following exponential equations. So 4 times e to the negative 0.2t plus 600 equals 1,000. So this one's a little more complicated than the first couple of examples because we have our exponential here, but then we have some other terms as well. So when we have an exponential equation that looks like this, our first step should always be to isolate the exponential. So, if we look back at the previous 2 examples, the reason we didn't mention that in these is the exponential in example 1 was already isolated, and the exponential in example 2 was already isolated. So that's why we didn't mention it for those first two, but in general, this should always be our first step, is to isolate the exponential. So we're going to minus 600 and minus 600 from both sides, and that gives us 4e to the negative 0.2t is equal to 400. We're not quite done isolating the exponential yet, so we divide both sides by 4. We have e to the negative 0.2t is equal to 100. So after we've isolated the exponential, we'll notice that it is just like examples 1 and examples 2. So now our next step then is use the inverse to solve. On both sides to solve. So in this case, our exponential is base e, and remember e is Euler's number, and the logarithm with the base e is the natural logarithm, so we're going to do the ln of both sides, so the ln of e to the negative 0.2t is equal to the ln of 100. The e and the natural log are inverses, so they undo each other. And that gives us negative 0.2t is equal to the natural logarithm of 100. And then step 3 is we're going to solve the equation. So now, in this case, this reduced to a linear equation. So to resolve a linear equation, we just get t by itself. So to do that, we divide by negative 0.2, and we divide by negative 0.2, and that gives us t is equal to the negative natural log of 100 all over 0.2. And that would be our solution to that equation. All right, so now let's take a look at our next example. So example 4 is different, once again, than the first 3 examples that we've seen. So this one is different because now instead of having one exponential, we have 2 exponentials. So now we just need to choose an inverse to use on either side. This is personal preference. I prefer to pick the logarithmic base of the exponent that seems more complicated. So in this case, I think x plus 3 is a little bit more complicated than negative x, so I'm going to use the logarithm base 4 on both sides. If you use a logarithm base 3, at the end, you will get a mathematically equivalent answer. It won't look exactly the same, but if you did a decimal approximation on your calculator, you would get exactly the same thing. So I used the logarithm base 4 on both sides, and the reason I picked the 4, as I mentioned, is I felt like the x plus 3 was a little more complicated. So then the logarithm and that exponential reduce out, and I'm just left with x plus 3. On this side over here, I have to use my power rule for logarithms. And the power rule for logarithms says that the exponent, the negative x, goes out in front. So that gives me negative x times the logarithm base 4 of 3. So I'm going to rewrite this as x plus 3 is equal to the negative logarithm base 4. I'm going to put that in parentheses of 3 times x. And the reason I do that is I want this to not look like something that I don't recognize. If I had the number 5 to the x, or if I had the number, up here, if I had the expression negative x times 3, I wouldn't leave it that way. I would rewrite it as negative 3x. The important thing we need to remember is that these two things are actually similar in the way that they work. The logarithm base 4 of 3 is just a number, right? If we ask our calculator, well, what is the logarithm base 4 of 3? It's going to give me some decimal approximation of a number less than 1. Okay, so this just represents some number. So we can treat it just like we would any other number. So if I needed to solve this equation, I need to get all of my x's on one side and everything else on the other. So I'm going to add log base 4 of 3x to both sides. And then I'm going to minus 3 and I'm going to minus 3. And when I do that, these reduce out and those reduce out. And that leaves me with the logarithm base 4 of 3 times x plus x is equal to negative 3. Then on this side, I now have a common factor of x, so I'm going to factor out my x. And when I do so, that leaves behind the logarithm base 4 of 3 plus 1, and that 1 comes from factoring out that x. If I multiply this back in with the distributive property, 1 times x gives me x, and x times log base 4 of 3x gives me the first term, equals negative 3. So then finally, to get x by itself, I divide both sides by the logarithm base 4 of 3 plus 1. So then that gives me x is equal to negative 3 over the logarithm base 4 of 3 plus 1. And that's my solution to that equation. And once again, this is my exact answer. If I only needed an approximation, I could go back to the original problem and I could graph each of these in my calculator. So 4 raised to the x plus 3 and 3 to the negative x. And if I graph, it's going to think for a second. And then I'll see my point of intersection right there. So then I can find that on my calculator by going second trace and choosing calculate, and then I want the intersection, so choice number 5. First curve, second curve, guess, so enter, enter, enter. My calculator thinks for a second, and it tells me that the x value is this number right here. So if I grab my calculator, x is negative 1.67 blah blah blah. If I go back to my home screen and I actually just hit my variable button, it will print that number when I choose x on my home screen. Well, let's compare that to the exact answer that we found. We had negative 3 over the logarithm base 4 of 3 plus 1. And we'll notice we get exactly the same answer. So we can verify that we got the correct answer on our calculator by checking and comparing the decimal approximations to our exact answer that we found. All right. So now let's switch gears and let's resolve a few logarithmic equations. So we want to solve the equation log base 3 of x equals negative 2. So to solve logarithmic equations, we're going to rewrite the logarithmic equation as an exponential equation. So we did this in chapter 5, section 3. So just to remind us, if we hop back to chapter 5, section 3, we had the following, which was we could convert something from exponential form to logarithmic form and vice versa by using this formula right here. All right, so we want to do this. So we have the following. We have 3. There's our x, and there is our b. So if we rewrite this in exponential form, our base is going to be 3. So we're going to have 3 raised to the negative 2 is the same as x. And now we just simplify that up a bit. So that gives us x equals 1 over 3 squared, and 3 squared is 9. So the solution to that logarithmic equation is x is equal to 1/9. All right, so let's do another one because they're not all quite that simple. So let's go ahead and take a look at our next example. So we're going to use that same technique where we're going to rewrite it, but the reason we were able to do that is, as we saw with the exponential functions, this logarithm was already by itself. So with logarithmic equations, if we have more than one logarithm, we're going to have to use our log properties to rewrite as a single logarithm. So the first thing we're going to do, step 1, is use the properties of logarithms to rewrite each side of the equation as a single logarithm. So on the left side right here, we're going to need to use the product rule. So that gives us 1 logarithm. So the logarithm of x times x plus 3 is equal to 1. So now that we have only 1 logarithm, we're going to rewrite in exponential form. So we didn't write it because we had the common logarithm, so don't forget, if we don't write the base, what is our base when it's not written? It's always 10. So our base is going to be 10, our exponent is 1 is equal to x times x plus 3. Our next step is we need to identify the type of equation and solve. So this type of equation, if we distribute our x in, we get x squared plus 3x, means it's going to be quadratic. So then, to solve a quadratic equation, we need to make it equal to 0. So we minus 10, and that gives us x squared plus 3x, take away 10, is equal to 0. And we can factor this guy. And we go x plus 5 times x minus 2 equals 0. And that gives us our two solutions, x equals negative 5, or x is equal to 2. The next thing we need to do is check if each solution is in the domain. So we need to remember that the domain of a logarithmic function is from 0 to positive infinity. But if we go look at each of the originals so we had the logarithm of x in the original, and we also had the logarithm of x plus 3. So this guy has domain 0 to infinity, and this guy, the plus 3 shifts it right 3 units, so its domain, or it shifts it left 3 units rather, is going to be from negative 3 to positive infinity. So if I do yellow for this one and blue for this one, the domain is the and. Of the domains of all logarithms. So if we do our domain then, we have 0, we have negative 3. So if I shade from 0 to positive infinity, that gives me this. And then if I shade from negative 3 to positive infinity, it gives me this. And the and is the green part, so right here. So the domain is 0 to positive infinity. So if I look back at each of these solutions, then this guy, x equals negative 5, is not in the domain. The only solution is x equals 2. All right. Let's take a look at our next example. So we wish to solve the natural logarithm of 4x plus 6 minus the natural logarithm of x plus 5 equals the natural logarithm of x. So step 1, we need to write each side as a single logarithm. So on the left side over here, we're going to use the quotient rule. And that gives us the natural logarithm of 4x plus 6 over x plus 5 is equal to the natural logarithm of x. So this one, since we have logarithms on both sides, we have the following special case that happens. When there are logarithms with the same base on both sides, the arguments must be equal. What that means is the following. Well, the argument of the logarithm on the left side is this, and that is the argument of the logarithm on the right side. So this tells us then that 4x plus 6 divided by x plus 5 has to equal to x. So when we have the same logarithm on both sides of the equation, the insides of the logarithms must be equal. So now this is a rational equation. So the LCD, there's only one fraction, is x plus 5. So we multiply both sides of the equation by the LCD, which is x plus 5. And then the x plus 5's reduce out, and that gives us 4x plus 6 is equal to, distributing the x in on the other side, x squared plus 5x. And we minus 4x, we minus 4x, minus 6, minus 6. And that gives 0 equals x squared plus x minus 6. So now we need factors of negative 6 that up to positive 1, so that's x plus 3 times x minus 2. So our two possible solutions are negative 3 or x equals 2. But now we have to find the domain of the equation. And this time we had 3 logarithms. So we had 4x plus 6, x plus 5, and x. So 4x plus 6 has to be bigger than 0. X plus 5 has to be bigger than 0. And finally, x has to be bigger than 0. So we minus 6, we minus 6. 4x is greater than negative 6. Divide by 4, divide by 4. So x has to be bigger than negative 3 over 2. And we have negative 5 and negative 5. X has to be bigger than negative 5. And this one, we don't have to do anything. X has to be bigger than 0. So if x has to satisfy all 3 of these, has to be bigger than negative 3 over 2, has to be bigger than 5, and it has to be bigger than 0. The and of all of these is x has to be bigger than 0. So once again, this negative solution is not in the domain. So the only solution is x equals 2.